Okay, so welcome everyone. Today we will continue talking about nonlinear equations. Last time we were talking about scalar nonlinear equations, and this time we will continue mostly with vector equations. And then we'll discuss a little about the theory of computer-aided analysis of mechanical systems. I will simply introduce some basic nomenclature. I will talk a little about how to describe mechanism at all. And it is as of today, that second part will be fully theoretical. So my aim here is to just make you know how it looks like, how to do that, what are some options, and this will be preliminary to the next part that will be next week, and we will talk about kinematic analysis of mechanism. Okay, I have to switch the focus. Okay, so let's start with nonlinear equations. So those are the slides that you have already seen, I hope. And the task on hand is to find a solution of a general equation in the form that some function or some scalar function, here is scalar function of scalar variable is equal to 0. And here is some concrete example. And this is all, as is written here, is called sometimes root finding. And it's reasonably important. And for us, we can find it at least in two places. So one is in implicit ODE solvers. We haven't discussed about implicit ODE solvers too much, but yeah, this is a very important area of application of those methods. And what is more important for us is kinematic analysis of mechanisms. And we'll discuss this today and tomorrow. And not tomorrow, but next time, in 1 week time. So about the solution of these nonlinear equations, we discussed firstly about brute force to just show how example implementation may look like. And then we went for more practical methods, so-called Newton-Raphson method or Newton's method. It has several names at least. So in this method, idea was to linearize equation, our nonlinear equation f of x around some point, like for example, xo, yeah, and then solve this linear equation because we know and it's quite easy to solve any linear equation. So solve this linear equation, and after solution, we'll get next approximation for our point. And our hope is to get closer to exact solution that it's 0. If you have noticed, this method is its convergence rate is high, so you can get quite fast to the correct solution if you will get there. Yeah, because there are cases where there are some rules where it cannot converge. So the rule of thumb is that it usually converges in most practical applications when our initial guess is close enough to the exact solution. Of course, there are some mathematical rules around here, but from engineering perspective, we assume that if XO is close enough to exact solution, then we will get the solution. If not, in most cases, it means that we cannot find the solution or this guess is wrong. Okay. Of course, we can use some hybrid method, but we'll not focus on this. So for scalar case, this was our linearization, that we replace our exact function with linearized function that just have two terms. Yeah, so this is a value of the function at the point of linearization xo, and then here we have this term when we have derivative of this function times some delta value. Yeah. And this came from Taylor expansion of the scalar function with scalar argument. Yeah, and simply by solving this around 0, assuming this must be equal to 0, we get to that scheme, that iteration scheme. Yeah. So it goes like that, that starting with x0, we can use this equation to iterate. So from 0, we can get x1, from x1, we can get x2, and so on forth. And until we will get close enough to 0. And of course, epsilon is our tolerance, so it's small value. So it works. So this is the core of the Newton-Raphson method. Do you have any questions about this method, or it is clear how it works? Okay, no comment, I assume it's clear. So now we'll get to a little more changing topic. It's about solving multiple equations at once for multiple functions. Yeah. So we will deal here with square problem. It means that here n, the number of functions is the same as the number of our variables. Yeah. Of course, we can also solve non-square problems, but this causes some issues, and we won't talk about this. So we'll only cover square problems. So the basic idea is that we want to meet that equation for all those functions at once. Yeah. So all those functions can depend on all our coordinates, and we want to find a set of coordinates that will equal all those functions to 0. Yeah. And because writing all those functions and all those coordinates, like here in explicit way, expanded from 1 to n, is a little cumbersome. So we will introduce a vector notation. Our bolded f is vector function, and it's column vector that consists of all our functions, f1, f2, up to fn. Yeah? And same applies to our variables. So we will group all our variables into column vector x, and it will contain x1, x2, up to xn. Why column vector? Because we'll just simply use this nomenclature. It depends from author to author, but at least in all the books that I have seen in mechanical engineering, for this purpose, column vectors are used. So we'll stick to that. So we start to talk about matrix calculus. Yeah. So the basic nomenclature is that we'll use boldface letters to differentiate between matrices or vectors and scalar values. Yeah. So boldface uppercase letters will be used for matrices. So those are arrays of dimension of 2. Column vectors or column matrices, yeah, they are 1D items, and they will be also described with boldface, but with lowercase letters, like lowercase x, lowercase b. Scalar will be used as standard, so with lightface letters, usually lowercase xyf, like here. AT, because it's transposed of the column vector, is a row vector or array, and bolded 0 is often used as 0 matrix. So using this nomenclature, we can rewrite the equation from previous slide in this compact form. Yeah, that simply vector function f as a function of all our variables x is equal to 0 vector. And as you can see, this equation takes exactly the same form as scalar equation, with exception that here we have hidden vectors instead of the scalars. So having some examples, it looks like that here we have two functions. There are functions of two variables, x and y. And if we put this into vectors, simply we have vector of variables x as scalar x and scalar y, so two-element vector, column vector, and vector of functions f of x. Yeah, looks also the same. Yeah, so we just put first equation is our first function, so we put it in the first row, and second equation is our second function, and we put it into second row. And we want to ensure that all that will be equal to 0 at once. So this is our 0 vector. Taylor expansion. So now to solve it, we'll use Taylor expansion for vector functions with vector arguments. Yeah, so it's almost the same like for scalar function. And here's equation. And the difference is that instead of standard derivative of scalar function f prime, like we have for scalar case, here we have this matrix, because this is matrix denoted as delta f. Yeah. So what is delta f? We'll talk about this in a second. Okay. And this is in practice quite standard Taylor expansion. Quite often Taylor expansion is written in slightly different way, because in practice we are making Taylor expansion around some point, and we assume that this value, this is a vector value, multivariable, it's close enough. It's a good approximation of the real function, if we are quite close to this expansion point, delta x. So here we have this delta x, and delta x appears here. So here we just write it in the way that this is delta. So delta is our target point minus our current point. And if we will set the delta and expansion is around xi. If we write this canonical form, assuming that delta is equal to that value, we get simply that equation. Okay, any questions? If not, let's continue. So what is this delta f? So this is a matrix that is partial derivative of f with respect to partial derivative of our variables. So it's almost the same like derivative of scalar function, but for many arguments. So, and by definition, this is matrix of all partial derivatives of f. This is often denoted by J, capital J, and it's called Jacobian matrix. That's why J. And we'll often we'll use this notation. So our Jacobian matrix of function f is equal to that one, and in explicit way, it's written like here. So this is for our case, this is n by n matrix. And it goes like that. That in rows we put all our functions. So in the first row we have all derivatives of first function. In the second row we have all derivative of the second function, and so on. And in columns we have derivative with respect to corresponding variables. So in the first column we have derivatives with respect to first variable, second column second variable, last column last variable. Okay. And in that way, we can create Jacobian matrix, then can be used for our Taylor expansion. As is written here, Jacobian doesn't have to be square matrix in general, but in our case, to solve it easily and use it with Newton-Raphson, it must be square. So our problem is square. So here is some concrete example to put it here to explain it better. So for our previous example that we have a vector of variables like here, and we have function like that one, simply we get, to get this term, simply we get first function and differentiate it partially with respect to first variable. So that's why we have here 2x, this is missing, and here we have cosine pi x, and here is my sine and this internal derivative. And for this term, because this is first row, second column, so it means that we take first function and second variable. So this is the partial derivative of this function with respect to second variable. And because y is only here, that's why you have -1 here. And same apply to second row. So this is second function, so that function. And with respect to x, we have y. This is non-existing, and here is plus x to -2. And here it's second function, second variable. So we have here only x left, and here we have -a to -y. So in that way, we can manually create a Jacobian matrix. Okay, I hope it's clear. And now with this Jacobian matrix, we can run Newton-Raphson iteration for vector values. Yeah, so we can approximate. We have this approximation xy. We want to get xi. We want to get xi plus 1, and this is just rewrite. This is rewrite equation from the previous slide. So this came directly from this Taylor expansion. And to get xi plus 1, we have to put our function at the current point on the second side, yeah, and we get this equation. We put delta here, so this is matrix, this is vector, unknown vector, and this is known value. Yeah, so this is standard in our problem that a times x equal to b, right-hand side. Yeah, and we must solve it from delta. There are many ways to solve it. Of course, we'll solve it numerically using MATLAB. Yeah, and after we solve it for delta, yeah, because xi is given, we can calculate xi plus 1. And then we check if our function is close enough to 0. If it's close enough to 0, then we'll stop as usual. Okay, so how to solve it? Yeah, so each step of Newton-Raphson iteration consists of 2 sub-steps. As it was written here, we first solve in our system like that, x equal to b with respect to the x noted here as delta. And then we calculate after the solution xi plus 1. So I don't know, what do you know about solving linear equations in practice? Yeah. But those systems are usually solved in the way similar to Gauss elimination. In practice, this is often used so-called LU factorization. If you are interested, I'm sure that you can find references in MATLAB and others. MATLAB uses so-called LAPACK package for this purpose. It's, I don't know, 50 years old library written in Fortran that it's used for efficient manipulation of matrices. And it's still developed and used because it's just bulletproof, so everybody knows it works well. So, and how to solve it in MATLAB? The best way is to use backslash operator. It's called ML divide. Yeah. So to solve ax equal to b, you must write something like that. That x is equal to a backslash b. Of course, there is always possibility to use inverse functions. Maybe you have seen this if you needed to solve linear equations. But this is not advised because of at least 2 reasons, because it's slower and less accurate. So there is really no practical reason to use it. Only use inverse when you need directly inverted matrix, because this is use different method and it doesn't calculate inverse. This is this node. The Jacobian is often sparse matrix, especially in the it will not have this setup in our kinematic analysis or analysis of our mechanism. And there are special methods that can deal with sparse matrices, that these sparse matrices that have mostly 0 enters. But we'll not discuss this here. We'll stick to dense matrices. Okay, and how it may look like. So, yeah, so here I have code. So here is code for later, but here is code for Newton-Raphson vector solution. So this function, Newton-Raphson method, I will upload it later on GitHub. Takes 4 arguments. So f, as you may guess, it's our vector function. J is Jacobian function, and you can also use, if you have problem with calculating this, you can also use, for example, symbolic calculations for that, or make it by hand if equations are easy. X is our initial guess, yeah, and epsilon is tolerance. This name, okay, it's not the best, but okay. And how it works. So here is this preparation phase. So firstly, we get the value of our function with respect to x, and then we calculate L2 norm of this vector, yeah, because we must ensure that all values of f are close to 0. If we are close to the solution, that's why we take norm of the whole vector to turn all those zeros into a single value. And here we have also the safety feature iteration counter that we want to ensure that we won't have infinite loop if the solution will diverge. Loop is almost the same like for the scalar case, but of course here we have this ML divide. So here we solve equation that jx times delta equal to minus f, yeah. So we get here this delta, this is first step, and then based on delta, we can calculate the next approximation of our function. And of course, then we have to calculate the new value, new norm to check in this step if it's close enough to our solution, and then increase iteration counter. After it ends, we simply check if we got close to solution or we get just iteration counter large enough to stop calculations. So if our solution is close enough, it's not close enough, so it means that it stops due to excessive number of iterations. We set our iteration counter to -1, so -1 here will be a flag that will tell us that method that doesn't converge. And here's very basic tests for our example. Okay, can you see, by the way, this code, or should I make this font larger?
I think it's fine.
Okay, great, thanks. So if you will examine this closer, this is exactly the equation that we have seen earlier on slides. So it was here, yeah. It is just written in vector notation, yeah. So because f is vector function and it takes vector as argument, x, yeah. So x is vector here. So it means that x1 is our first variable. So it corresponds to this scalar x here, and x2 is our second variable. So it corresponds to our scalar value y here, yeah. That's why we have here x squared minus y plus x times cosine pi x. Yeah, exactly same here. And here we have xy plus a to minus y minus x to minus 1. Yeah, so exactly that stuff. And here, this Jacobian was calculated by us analytically. So we also put here in analytical way. And in the same manner, it accepts scalar value, not scalar, but vector value x, and it returns 2 by 2 matrix. Yeah. So if you will check it carefully, this is exactly that matrix. Yeah. So this is our matrix, and because this is simple check, yeah, or simple test, it's not so obvious, but we are expecting from this solution to get 1 and 0. So from 1 and 0, this function will be 0. Yeah. So we put some rough tolerance 10 to minus 4, and we'll just test our algorithm, then check error with respect to expected value, and see if it converges. Yeah. So I'll clear the workspace to see how it works, and you will simply execute it as any proper test. It returns no error. Yeah, so it means that test passed. So norm of the error is smaller than our tolerance. If you want to know what is the exact value, so we get error at the level of 1 to 10 minus 6. Yeah, and here we can see that after just 4 iterations, we get the solution from 2 minus 1. Yeah, it's pretty close to our exact solution that it's 1 and 0. Okay, any questions about any of those codes? Okay, so this is the way it works. And of course, MATLAB is designed for matrices, so that's why we were able to write this whole method quite easily. And in practice, despite it is very simple, yeah, this method is very simple, it's often used in practice. And it's not implemented in MATLAB, at least not directly. And I think that the main reason, I don't know that it is implemented, because MATLAB has methods that can find zeros. And for example, one of this method is called f0, root of nonlinear function. Yeah. So of course, MATLAB has function for many problems. Yeah. So why not to use, for example, f0 instead of our Newton-Raphson? And the main reason for that is efficiency. So we know that for some cases, we might have problem with Newton-Raphson, and this is the main reason I believe why it's not implemented directly in MATLAB. It is not exposed directly. Because in MATLAB, one of the main focus of their algorithms is the robustness. Yeah, so they want to give user algorithm that maybe it's not the fastest, but for sure will give the solution for a wide range of applications. So that's why there is this f0, and it will be simply much slower than this raw Newton-Raphson iteration. And from other sources, we know that in our applications, like this kinematic analysis that will perform, Newton-Raphsons behave well. If it's designed correctly, it behaves well. And in most cases, when it misses to provide solution, it means that there is something wrong with our mechanism, not with our algorithm. Okay, so it has practical importance, this method. And here we apply it to some simple mechanism. It's designed as hands-on, but I believe due to the nature of the Zoom and because I'm present here, I will just show you solution. I hope that you analyze it or even solve it by your own after this lecture. So let's see, what is the task? So here's a mechanism. It's quite simple mechanism. It has just two bodies, yeah. So this is one link attached here to the ground at point A, yeah, and it's attached to this circle at point. Okay, so this point is not noted. So at some point, and this point is shifted from the center of the circle with the length A. Yeah, and the circle has radius r, and the distance between the center of the circle and point A is denoted as d. And the question is, to find phi2 and distance d when phi1 is provided. Okay, so this is task, and how to solve this task. First of all, we need to somehow describe this mechanism in the form that it's understandable by a computer. And the easiest way to do that for that kind of mechanism is to write so-called loop equation. Yeah. So knowing that A is always put it here, just using those physical properties of this mechanical model that A is always put it here and on the ground, yeah. That point has also fixed position with respect to the circle. Here is the center. We also assume that that the circle is always in contact with ground. We can simply write. Then we know that, for example, that. Okay. Okay, now it works. Yeah. So that vector, let's call it B. Yeah. Plus that vector. Sorry, I'm not very great with drawing with, especially with mouse. Yeah, I hope it's clear. Yeah. So that vector B from that point A to this point plus vector A from this point to center of the circle, plus vector that one, we can call it vector R, yeah, and plus vector D, or because D is denoted here, so let's say it's minus D, yeah. It's always equal to 0. And it's because of the geometry of this mechanism, yeah. Because, yeah, so it's always valid when the circle is in contact with the ground. This vector equation is always valid. That's the sum of all those vectors is equal to 0. And that equation for those 4 vectors is written here, yeah. So those 2 terms, okay, those 2 terms is vector. This is vector B, yeah, and we must put it in some reference frame. So our reference frame is simply X and Y, yeah. So this is our reference frame. So this is B vector. This is A vector, yeah, and this is R minus D vector. R minus D vector. Yeah, because R has only R component, so this is R vector and this is minus D vector. Okay, is it clear? I hope it's clear. So this is the way to define that equation. This is algebraic equation. It's important that this is algebraic, and this is so-called constraint equation because it constrains the motion. And because the motion is constrained, we can calculate phi2 and d when phi1 is provided. Okay. Any questions about this problem? Good. To solve it with Newton-Raphson, we then calculate Jacobian matrix. So we know that our first first coordinate, first variable is phi2. So simply that equation differentiate with respect to phi2, only this term applies. This term appears because this is 0, this is 0. So we have here minus a sinus phi2, yeah. And the same for second equation, only that this term is differentiated with respect to phi2 gives a non-zero term, a cosine phi2. And with D, it's even simpler. Here we have -1, and here we have no D, so everything is 0. Yeah, so this is our Jacobian matrix. Yeah, and based on that, we can write this code. Yeah. So those 3 values A, R, and B are taken directly from the figure. Yeah. So so those are the dimensions of our mechanism. Phi1 is initial. It's another assumption. It's provided here that phi1 is equal to 30 degrees. And because cosine signs in MATLAB are usually operate on radians, so we convert this value from degrees to radians with the built-in helper function dectrad. Because we are using Newton-Raphson, we need some reasonable starting point. So I choose 0 and b plus a. Yeah. So 0 from 0 from phi2. Yeah, that assume that this might be just maybe 0. So this vector a is put it horizontally. Yeah, not like it's. I assume that this is reasonable assumption. And d is equal to a plus b. Okay, maybe we can get better, but it should be close enough. Here we have those functions. Here I put constraints. So our vector function f, a separate function here. So u here is denoted as our vector. So here we decoded. u1 is phi2, and u2 is d. And here is just expression. And this is rewritten exactly that equation. B cosine phi1 plus a cosine phi2 minus d, and similar here. Here is second function. This is Jacobian of our f function from also vector u. we also only use phi2, and so this equation is simply that one, that matrix written as a function. And here we use anonymous function just to expose u, because this is the form that is expected from Newton-Raphson method. It only expects u. And then we just call it. Yeah, so we set small tolerance, and we call Newton-Raphson fju. And here is just a message that will show us, that will give us solution in a readable form. So clear output, clear workspace to see, and just call it. And also take 4 iterations from that point, and it provides us that for phi1 equal to 30 degrees, the distance d is equal to 10.4 meters. This is 10.4 meters, and phi1 is equal to minus 30 degrees. Yeah. So minus 30 degrees, it means that it's almost like on this this figure. Yeah. Because in the way shown here, the angle is simply denoted as a positive value. And if we'll go, okay, that one it's not so easy to draw. Because so in this direction, we can calculate just simply minus phi2. So counterclockwise. Okay, any questions about this example? Okay, so we already can see that Newton-Raphson method can be used to provide some kinematic analysis for mechanisms. Like here, we start with one variable, and then we were able to solve it reasonably easy, because it's quite easy to form this vector equation. Reasonably easy get another kinematic values from that analysis. Okay, so now I just copy paste here assignment slides from the last time. So as you can see that this example is quite similar to the example that we have just seen. And my question is, if you have any extra questions to it? Any doubt? Or hopefully after seeing that example on the previous slide, it is reasonably easy to solve it. Okay. Okay, if there is no comment, I assume that it's now reasonably easy to solve it. So we'll continue to the next part, and now it will be mostly only theory. And I hope it will be reasonably clear what is the message here. So to get used to computer analysis of mechanism, okay, start with Nick Ravesh, because this is the book that we are following. And know that this book was written in 80s of the last century, so it's already quite old book. So even the idea of computer-aided analysis wasn't so widespread. So now it's quite obvious that you want to design something, we must start with the computer, create the code, not create the code, but create a model, first plot it and then analyze it in the way. But in those times, I think it was still quite common just to use pen, paper, and make technical drawings and perform some graphic analysis. But of course, the aim is still the same. So we want to use computer to aid our analysis process in the way that we can simulate the behavior of the product before it will be created. Yeah, so because in the old days, of course, we must prepare some prototype. And then if it's not working, that it was needed to prepare another one, and of course it was time consuming. And now it's far easier to create just so-called virtual model. Yeah, and this branch that deals with mechanism, and so from areas of mechanical engineering, it's called multi-body mechanical system. Yeah, so it's multi-body system analyzes multi-body system dynamics. So this multi-body term is here quite common, and of course, this multi-body came from the fact that we have usually multiple bodies. And the way that we tackle our problem. So when we have the whole mechanism, we disassemble it mentally into various bodies, and then we try to analyze how they are connected together. Yeah. So this in multi-body system, this mechanical system is defined as a collection of bodies. Yeah, like here we have one body or two, depending if we think that if we assume that the ground is separate body that cannot just move or not. Here is four-bar mechanism, four-bar linkage, yeah, the most used mechanism for motion transmission. And here is so-called another famous mechanism, slider crown mechanism. Of course, that is known the best from internal combustion engine, yeah, and it changes the linear motion to rotational motion. And then we assume that those bodies can move with respect to others, yeah, and this motion is described with constraints. And constraints can take different forms. So yeah, so we assume that any mechanism that is in our interest can be represented systematically as multi-body model. And important things are bodies, how they are connected together. So that here is joint that looks like revolute joint and some other joints, yeah. The inertial characteristic of the bodies. So as you can see here, they have the shapes of this X or potatoes. Let's say that we have Easter, so this is X shape. Yeah. So because if we don't perform, we don't deal with contacts, the exact shape is not so important. And inertial properties are far more important. Type and location of joints and physical characteristic of other things like forces, springs, dampers, and everything else, torques. And we assume that if we have that type of the description, that we have bodies, connections, forces, and other characteristics, we can describe that model with computer, and then computer will generate equations of motions for us and then solve it. So we just must prepare the model, run analysis, and then we can see how it moves as a whole. So here's a little word about methods of analysis and how they're divided. Of course, everything here is involved in mechanics. So this is the study of motion, yeah. And maybe you remember that, at least I also learned that it is divided traditionally into statics and dynamics, or sometimes into statics, kinematics, and dynamics, depending how do you create this division. If it's because sometimes the dynamics is plurally divided into kinematics and kinetics. While in kinematics, we are not interested in the force, only on the motion. So we talk about the usually displacement, velocity, and acceleration. And kinetics is then in study of the motion that relate the forces. And here we have these differential equations. And in practice, this is the most common analysis. However, kinematics also provides a lot of information and it's far faster. Yeah, of course, simplifications, because those X-shape model, it's not really like the full model, the real model, but like everything with modeling with mechanics, yeah, the simplification is the key. But we want the simplest possible model, but not too simple. And the old approach was to use graphical techniques. However, I'm not old enough to remember how to use graphical techniques. I never learned this. Okay, so methods of analysis. Yeah, so we want to solve it using vector algebra. You have seen already this on an example in the Newton-Raphson section. Yeah, so we have some kind of mechanism. And then we need to write some constraint equations. Okay. And as in the previous example, this vector equation that define the structure of the mechanism was used for generating constraint. This is quite universal method, and here it's also used. Yeah, so we can also create this vector box here. This vector, yeah, this vector here. Yeah. So here we have, for example, this A vector, B vector, yeah, and also called D vector, yeah. And we know that A plus B plus D for this mechanism, no matter what is configuration, will always be 0. And this fact is written here. So here is, of course, A vector. Here is B vector. And here is D vector in our reference frame X, Y, denoted here. Yeah? And as previously, here we can find a solution that, for example, if phi is given, we can calculate another properties, another terms like unknown angle theta and unknown length d. By the way, here you have solution for assignment, I believe, at least for some initial angle phi. So you can check if your solution is correct, at least for this angle, because you should get the, close enough to that solution. Okay, so because we discussed this in more details previously, yeah, I think that we can get further. So then we can also perform velocity analysis. Simply, after kinematic analysis, we know all those values, phi, theta, and d, yeah? And to get velocities, we simply take this equation and differentiate it with respect to time, yeah? So this is the differentiation with respect to time of this vector function. And then in the similar manner, knowing, for example, omega, yeah? And by the way, because omega is in a different direction than phi, yeah, we know that phi prime is equal to minus 1 radian per second, yeah. But having this phi prime, yeah, we can calculate theta prime and d prime, yeah. And by the way, because d is this length, then d represents the velocity of point B, because it's assumed here that B only moves horizontally. And this analytic approach is known to be quite easily implementable on the computer. So this is the root of our computer-aided method for mechanical system, and this especially for kinematic analysis. Any questions or comments to this part? Okay. So how to write those equations? Yeah, because of course it sounds great as an idea, yeah. But for example, for this mechanism, yeah, we have written those equations by hand, yeah. So for us humans, as you know, it's quite easy to see how this mechanism is built, yeah. But how to provide this knowledge to computer? So here we have this trade-off between efficiency and versus simplicity. Of course, it's not so easy, it's case dependent. But in general, what we want to write, our goal is to have this general purpose program, yeah, that can analyze, a variety of mechanisms. So it doesn't matter if we have this 4-bar mechanism, we have the car, train, or whatever we can think of. We want to be able to model it in our software. That's why it is called general purpose. And of course, we don't want to deal with writing equations. We just want to create model, tell how it is, what are connections, what are forces, and then we want to get results. Yeah. So that's why we need some bodies, connectivity between bodies, joint types, forces, and some other properties like inertia, geometric properties, and some others. Then all the equations must be generated by the software, and the software must also contain some solver that then will solve it numerically and just provide readable information for us. And as written here, efficiency depends, and also simplicity of our equation depends on the choice of coordinates. There are multiple choices of coordinates, so we can write them in different way. Yeah. If you have some courses on mechanics, I believe that you often use generalized coordinates. Relative coordinates are all another common way, and another also way to describe is to use Cartesian coordinates. Let's say that I won't discuss it here. You will see it clearer when you will see how those coordinates are applied. Yeah. So generalized coordinates. So with generalized coordinates, use only the number of coordinates that is equal to the number of degrees of freedom of our system, of our mechanism. Yeah. So for four-Banach linkage that it's shown here on the right, it's enough to provide only one coordinate. Yeah, so I can provide any of those, for example, angles, and then we have fully described system. Yeah, so if I have this phi defined as our coordinate, then that's all. Yeah, this is our coordinate. It's free coordinate, so we don't need any constraint equations. Yeah, and we can, if we know phi in time, or a derivative of this phi also, yeah, velocity and acceleration, we can define any other coordinate here. Like we can define all those angles or the velocities, position of the joints, and everything else. So having phi, yeah, we can calculate others. For example, using those equations. Yeah. So from this equation, we can directly calculate theta 1. Yeah. From this equation, having phi, we can calculate theta 2. This is just simpler equation, not to provide theta 3 in this obfuscated form and just with, but we still can put theta 1 from here, theta 2 from here, and then we calculate theta 3. And here, RDS and L are left of these links, RDS and L. So this is the description in general coordinate. So this is, we use minimal set of coordinates. This is nice because the number of coordinates is small. Also, for example, differential equations or other equations size is small. However, kinematic description is quite complex and it's highly nonlinear, as you can see here. Okay, so can we do this in different way? Another choice is to use relative coordinates. Yeah, so we use some redundant coordinates because still the system has 1 degree of freedom. Like and relative coordinates are written in 2 main ways. Yeah, so either, for example, like here we use angles of those 3 bodies because we have 3 links and we use 3 angles. Yeah. We use this line here. Those angles are denoted with respect to global reference frame because all those lines are parallel to each other. Another way is to write them with respect to another bodies, and in that way, alternatively, they could be written like that. Yeah. Let's say that this is phi to, let's say, prime. So this is with respect to the motion of the first body, and that one is with respect to global because there is no another reference here. And this phi 3 prime can be written then that way. Yeah, both ways are similar. Here, this is just showing the way that those coordinates are written with respect to the same basis, global coordinate. Nevertheless, here we have 3 coordinates, yeah, and of course they are not independent, yeah. Those are not general coordinates. We have still 1 degree of freedom because mechanism doesn't change. So we need 2 constraint equations, 2 algebraic constraint equations, yeah. And we can write it like here. There are reasonably simple equations, and of course this is our well-known vector equations for our mechanism, and that say that this whole mechanism can be shown as closed loop. Yeah, so this is closed loop equation. So this is our R vector, this is D vector, this is vector S, and this is vector, let's say L. Yeah. And of course this is R, then this is D, this is S, and this is L. Yeah. So what is characteristic of this method? We have more coordinates than for generalized coordinates. Yeah, they are dependent, and we have to include some constraints. However, there are not too many of them because for this case we had 1 generalized, we have 3 reference, and so the number of algebraic constraint equations is equal to 2. And this equation, if we compare it with let's say those equations for generalized coordinate are simpler, and the same will apply to differential equations of motions. Differential equations of motion. And then we have Cartesian coordinate. Yeah, in Cartesian coordinate we have really a large set of coordinates, and in this approach, we for planar mechanisms like here, we just assign always 3 coordinates for each body. Yeah. So we have body, and then we assign coordinates for it that fully describe that body. Yeah. So to fully describe that body on the plane, we need 3 coordinates, and those coordinates, like here, it's shown, are chosen as x and y position of the center of mass. Usually it's center of mass. Like here we have center of link, and the angle with respect to global reference frame. Yeah. So for this simple mechanism, we have 3 bodies, and it's planar. So for 3 bodies, we have in total 9 coordinates. As this mechanism has 1 degree of freedom, it means that we need 8 constraint equations of motion. Yeah. So we need 8 algebraic equations. Yeah. So this is our full vector of coordinates. This should be bolded. Sorry about that. So, and of course, those are coordinates of the first body, second body, third body. Yeah, 9 of them. Only 1 is independent. So we need 8 equations, constraint equations. How to write those constraint equations? Those equations are about the joints here, yeah, in those points. Because that equation, what is written here is written here that that vector is equal to 0. Yeah. So this is that equation. Yeah. So it means that n minus r2 cosine phi. Yeah. If you analyze it carefully, this is the vector that points to A. So this is the vector for that joint. Here we have another joint. So this is joint B. So that part is that vector, yeah, and that part is that vector, yeah. So this is vector B in reference 1, and this is vector B in reference 2, written in body 2, yeah, local body 2. So this is this B1, and this is B2. And of course, it simply states that point B is here. Yeah, so it doesn't matter if we search for point B from that or that perspective, we'll end up here. And that's why, because the sum of those vectors is equal to 0. And here we have join and point C in similar way. And here is join at point D with respect to ground. Is it clear how those equations are created? Okay, great. So what we can see here, we can see that here for Cartesian coordinates, we have the largest number of coordinates because for this simple example, we have already 9 coordinates. We have a large number of algebraic constraint equations, but as you can notice, it's very easy to select coordinates because coordinates are always Cartesian coordinates, three Cartesian coordinates for each bodies. Yeah, and if we know connections, it's also very easy to generate constraint equations because, as you can see, they have a similar form that is simply repeated the same way. Yeah. So here you can see that simplicity is key for this method here. And also, if you take a look also more carefully on this, you can see that there's sparsity pattern assembled here, shown here, because, for example, to describe that equation, only bodies 1 and 2 are involved. Yeah. So that constraint equation that describe point B include only those two bodies that are connected at the point, and the same applies to another joint. Yeah. So like here for joint A, we have only coordinates of body 1. For joint B, we have only here coordinates here. For joint and point C, we have also coordinates of body 2 and 3. And because at some point we will generate a Jacobian matrix for those algebraic constraints, it means that a lot of derivatives will be simply equal to 0 because they will involve coordinates from different bodies that are not shown here. Okay. So for the Cartesian coordinates, for any configuration, one of those 9 variables coordinates might be specified, and we can get any other 8 of them. Yeah. And here we have some general conclusions. Of course, this is case dependent, but here we have comparison of coordinates, generalized, relative, and Cartesian. So of course, okay, I will switch the pointer. Of course, number of coordinates for here is minimum because it was like 1 here, and it's always minimum. Here is moderate because we have to add some more usually. And for Cartesian, this number is large. It's reasonably large. And the same will apply to differential equations because different number of differential equations, it's connected directly with number of coordinates. So this is the same, exactly the same property. And number of algebraic equations, it goes like that. That of course here we had none because if we have the minimum number of coordinates, we don't need any constraint. Here just there are few of them because we have few extra coordinates, and here there is large number of algebraic equations. However, nonlinearity, yeah, here is high, here is moderate, and here is low, because all those equations look similar, yeah, and they only include a limited set of coordinates. So, all this characteristics directly goes to this, that the derivation of the equations of motion, it's hard for generalized coordinates in general case, yeah, because it's reasonably easy to do this for bark linkage for us, but you have, for example, with a full car or some train, then to force computer to generate these equations, it's quite tricky. It's not so hard here because we have those loops, so we can try to somehow follow them, but still we need to perform some topology analysis. And for Cartesian coordinates, it's simple because no matter how this mechanism looks like, we always assign coordinates to each body. And then we have a certain set of routines that generate our equations for the various types of joints. Efficiency. So of course, this is usually efficient. This is also efficient, and this can be not as efficient. for sure, we need to take sparsity into account to make it anyhow reasonably efficient. Yeah, but often the simplicity wins. So yeah, and all of that goes to program development. It's connected with this reverse applications motion that it's hard to develop it and how to include new features. This is relatively difficult, but here it's reasonably easy due to the simplicity of description. And that's all for today in practice. And by the way, I think that one of the most commonly used multi-body softwares is this MSc Adams. Yeah? And this software also uses, for example, this uses Cartesian coordinates in general. However, of course, there are other software, like for example, Recording or Meva software used here at our universities, and they are mostly using relative coordinates, mainly because of this reason. I'm not aware of any software. I'm sure that there are some softwares, for sure, at least some research software that use good general coordinates, but they are not so widespread and wide known because of this difficulty. Okay, so that's a bit everything as for today. Do you have any questions? Any comments? Anything? Yeah. That's yeah. What is our time? Okay, so we have about a little longer than the hour it takes. Yeah,